Welcome back to Simulating Nature in Scilab. This is episode 3, one last look at old school, constant rate, growth and decay. This is as far as your calculator or spreadsheet is likely to ever take you. After this, we can model what nature really does. At the end of episode 2, we installed an interest loop on the bank model. This made the balance trend upward over 10 months. Now we will get rid of the deposit and withdrawal schedule. We will just watch the interest loop over time. This is probably the simplest circuit we can make that does anything interesting. When exploring in math, we can start with all ones. We load the account with the starting value of 1. The interest loop will get a gain of 1. What will the account do? We use the 1000 fractional samples per period idea from episode 2. The account starts by taking in 1 divided by 1000 for the first update. The second update will be 1.001 over 1000, and so on. Let's see what we get. We get a nice, gently increasing curve starting with a value of 1 at time 0. There is no deposit or withdrawal lumpiness to it. What do we have at time 1? Looks like 2.71. Must be important. We started with a balance of 1. Our feedback gain was 1. We let the model run through one time period. At time 1 we got this odd number. This is E, one of nature's coolest numbers. E will be part of everything you do, all the days of your life. How about the slopes near certain points? The slope at the origin with y equals 1 looks like 1. Equal rise over run. How about the slope at y equals 2? Looks like it could be a 2 to 1 rise over run. This agreement between height and slope may be why the curve seems so pure. The exponential growth curve has slight rule characteristics. It creates a relationship between our counting number world and another number world that can be called the percent difference world. The curve can multiply and divide, and even do powers and roots. Let's see an example. We multiply 2 by 3 using the curve. We find 2 on the vertical scale. Trace across to the curve and down to see around 0.69 on the horizontal scale. Now we find 3 on the vertical scale. Trace across to the curve and down to find around 1.1 on the horizontal scale. Instead of multiplying 2 by 3, we add 0.69 and 1.1. We find our sum of 1.79 on the horizontal scale. From 1.79 we trace back up to the curve and across to see around 6 on the vertical scale. In the counting number world we multiplied, but in the percent difference world we added. On your calculator, moving from the counting number world to the percent difference domain is done by pushing the ln button, taking the logarithm of the counting number. Going back is called exponentiation. It uses the e to the x button. Exponential growth is the simplest type of biological growth and covers those species that don't use sexual reproduction. We'll do one example of exponential growth the old fixed-rate way. A biology instructor says there is a bacteria culture that doubles its population in 1.5 hours under good conditions. From this one point on the growth curve, produce a section of the growth curve for this bug so that growth factors based on other reasonable time points can be estimated off the curve. Future value over present value equals our number e to the r, t. Let's talk about what this equation does. An equation is supposed to show the same thing from a pair of useful viewpoints. On the left without any special function in front of it is our growth factor, like 2, for when the bacteria have doubled. Future value divided by present value. What is on the other side? Rate and time trapped as an exponent of E. It is total work done on both sides of the equation. What can we do to untrap rate and time so we can solve for rate? How about take the logarithm of both sides? That looks better. The logarithm of 2 is 0.69. Now for the right-hand side. Why did logging E make both disappear? It was like taking a trip across and down on our universal growth curve, then back up and back across along the same path to where we started. This 0.69 is now sitting across the equal sign from our rate and time of 1.5 hours, and we are safely back in 8th grade. We divide through by 1.5 and see our value for R, 0.46. This is what we put in the growth curve generating circuit to make other colony growth factors available for other reasonable time points. Now for negative feedback and decay. We keep 1 as the starting value of the account. This time we set feedback to -1. The first thing the account will do is take in the -1 from the gain block and divide it by 1000. This will cause the starting balance to begin dropping. Here is the curve. We begin with a sharply falling curve. The initial slope seems to be aiming at a time base point of 1. But we are soon flattening out. What percent of the original balance of 1 do we have at time 1? 0.36 and something. Does this number mean anything? Could it be 1 over E? It is. How about the slopes of the decay curve beyond the starting point? Like the growth curve, the decay curve seems suspiciously well behaved. At a y value of 0.5, the curve slope is around -0.5, half the fall over the run, and so on. Again, we have agreement between slope and value. We have a name for the time to cool or discharge to 36% along this standard decay curve. It is called one-time constant. Let's look at the overall decay curve. After 5 time constants, we are pretty much at the bottom. Engineering students usually take 5 time constants as the time for a full enough discharge. Let's do one quick example of old school, fixed-rate decay. A physics teacher prepares a cup of tea, 100 degrees Fahrenheit above room temperature, and covers it. This is to prevent evaporation losses, while keeping that part of the cooling function that is mostly from diffusion conduction. The tea warming the air through the cup walls. 50 minutes later, the temperature of the tea is measured. It reads 33 degrees Fahrenheit above room temperature. She wants a decay curve for finding other temperature levels after other reasonable cooling times. She wants R. RFV over PV is 33 over 100, or 0.33. R percent of an hour is 5 over 6 or 0.83, and this is used for our time. We do everything the same as before to get R. Hopefully R will turn out negative, as this is supposed to be a decay problem. Ln of 0.33 is -1.1. We divide through by 0.83 and we have R equals -1.33. We put our -1.33 in the feedback scalar and see the curve. All the reasonable combinations of time versus degrees above room temperature are available to us. That's it for the frustrations of old school. Now, with our modeling software, we can handle varying growth and decay effects on the fly. This is what nature really does. See you next time for episode 4, Retirement Account and Debt Load on a Business. Scilab is software buy-in for the world's community. Help them with dollars, publicity, and contribute code. TTS Voices copyrighted 2014 and licensed by LinguaTech, GmbH. Visit them at linguatech.de. Text and graphics copyrighted 2019 by William Rhodes Design.